So my goal today is to finish off chapter 3, and we still have some topics in which to cover. This is kind of the main list of things. So, oops, 2 headings. Let's look at one particular question, which is really it's connected to the units used. Oops, try that again. The units used for X and Y, and how they affect regression. So, suppose you were measuring something in X, the explanatory variable. Suppose it was measured in feet. So you measured the length of a snake in feet, and you have its weight, and you measured its weight in pounds. And so as a snake gets bigger, not surprisingly, it gets heavier. So you'd expect some kind of data like that, right? That seems reasonable. And let's say in this data that the predicted weight was I'm trying to think of this 1.2 plus 3 times I'm just gonna have to call that length. So this is length. How long it is and its weight. And the weight is, of course, is called the response variable. Well, you got your data. That's what a straight line looks like. Let's say that the correlation coefficient was 0.9. That would give you an R squared of 0.81, or more likely, it would be called 81%. Now, if you decided to change the units, so instead of measuring the length in feet, you did it in inches. And instead of doing the weight in pounds, you decided to measure it in pounds. This equation would change, right? Which is not a surprise, right? 3 feet, putting 3 in here is not going to be the same as putting 36 in, right? So the equation would change. What doesn't change, however, is that R and R squared are still the same numbers. That might seem surprising that if the equation changed, well, because the data points will change, won't they? If a 2-foot snake weighed 5 pounds, then a 24-inch snake would weigh 80 ounces, right? It'd be 2 different numbers you'd be using, right? 2 different plots. But R and R squared are still the same number. It's important because what that tells us is that it doesn't matter how we measure the thing. The connection that's there between the 2 variables remains the same, and the strength of it, which is what these numbers are measuring, is the same. And that's helpful because if it wasn't true, couldn't you measure something in ounces? And if you didn't like the answer, you'd measure it in pounds. And if you didn't like that answer, you'd measure it in kilograms, right? You just find some unit of measurement that made the data look better. That wouldn't be very good if that was true, right? So the fact that it doesn't care is actually quite important. I think, Ian, you got a question that was something like, what would happen to it? To say the answer is it would be exactly the same. Let's look at 5. the effect of outliers on these regression lines. And the effect they have might surprise you. So we have our X, we'll have our Y, we won't put any story on it, so we can just focus on the data. Let's suppose we have our positive linear guy, and your data looks like that. If any data point has a large X value, and we call these points this is a special name, influential points. Good name. They have a lot of influence. Right. So imagine this data set the way it is right now, and you got that as the equation, right? Now, suppose there was another data point with a really large X value, an outlier, right? Up there. Now, that outlier is called an influential point. Because it has, relative to the rest of the data, would you agree it's got an extremely large X value? Now that influential point, it's got two hats on. It's also an outlier. It's no longer an outlier because it's called an influential point. Isn't an outlier, isn't an influential point just a special version of an outlier, right? That's the only thing that makes it different, right? I mean, if I had a data point where my finger is, wouldn't that be an outlier? But it wouldn't be called an influential point, right? It doesn't have any special name. But this guy is. So you're clear about it's still an outlier, but it's a special version of one. What does that do to the data? Well, the name influential point tells you kind of what's going on. Oh, by the way, let's say that the R value in this case was 0.7, right? If you had this extra data point and you put it in your analysis, you would change only one of these two things. Would you agree that the straight line going through that data point, the green ones, is pointing in the same place that R is roughly, right? There's not a lot of difference. So the result is that it has no effect, no noticeable effect. Maybe that'll be a 2.1, but nothing major, right? What it will have an effect on is your R value. And this is what is counterintuitive to a lot of people. The R value gets bigger. It's only 1 point, yet it will have a noticeable effect on the R. In fact, won't it make you think that your data set is actually really good? When in fact, if you ignore it, can you see it's just okay-ish? But now it's good. And so when you are doing regression, right, where you're taking data, making a scatter plot, getting an equation, right, doing all those things, if you have an influential point, you have to be aware that it's going to make this number much larger than reality says it should be. So you can see that influential point is a distortion of the truth. But a lot of people like those points because don't they make their data seem much better than it truly is? You could, for instance, if you were a scientist who truly believed that something was true and you got your data and it looked kind of not really great, but you had one really good influential point, can you see the effect of that would make your line point towards it and it would make your R value reasonably big, and you would publish without showing the data because you know it doesn't look good. Hey, I've managed to find that there's a strong correlation between whatever this is and that, and to prove it, my R value is 0.8. And people will go, oh, that's pretty good. And then they look at the data and they say, wait a minute, it's just a blob and one big number. And the further away the X's are, right? So if it was up here where my finger is, right? If that influential point was here, it would be even more significant. That might go up to 0.9. So you can see that we have to be aware of these influential points. They have no, as long as that data point is in the same direction as the rest of the data, it won't change the equation of the line, but it will change the R. And of course, if you change the R, don't you automatically have an effect on the R squared because it's 0.85 squared. So right, we fix those two guys. Does that seem unusual that that property is true, that one data point could have such a large influence on the whole process? So the moral of this story is outliers are dangerous, right? They do bad things. Now, that's only one example of what an influential point might look like. Here's a totally different effect. It's still an influential point, but I'm going to put it in a different location. So imagine this is the same data as we had the first time. Right? And my influential, I'll put the equations back in. Right? So the straight line looks like that. And the correlation coefficient is still that. And I'm now putting my data point down there. You see how it's still an influential point. You agree it's got a really big X value. Okay, there are two things it could affect. It could affect the equation of the straight line, right? That's the straight line we own with the green dots. The minute you add this one, it could affect the equation of the straight line, and it could affect the R value. In fact, it does. What effect do you think it has now on the R value? Does this get bigger if you use that influential point, or does this now get smaller in this situation?
Smaller.
Smaller. Right, so it might go down to 8.55. Now, in that case, isn't this influential point making your data look weaker in the relationship world? And really, it's only one data point, maybe out of 100. What effect do you think it would have on the equation of the line, if any? Right now, the line looks, I'll put the line in. This is what the line would look like if you just used the green data, right? What do you think it would look like if you had that influential point? Oh, okay. I think of this as like a little magnet. And what it does is it will bend the line a little bit towards it. You know, not a fantastic amount, but it will be noticeable. Do you see how it moved the equation? So the numbers might change. Well, they will change. They might become 1.8 plus 2.7x, right? You see a little bit of bending, a little bit of straightening off. And so the influential point has a noticeable effect, right? You can tell that it's done something to the equation, even though it's quite minor in some ways. And it has a very noticeable effect on the R value. Are we good? Yeah. Any questions about that? Oh, okay, cool. Here's my little list. There we are. So we've talked about the effect of outliers on regression lines. Let's look at some of the common mistakes then that we have made. Well, let's look at one that's called extrapolation. We've talked about this before. Right. Extrapolation is essentially what happens when you use your model when I say you use your model, I'm talking about using this equation, right? The one that looks like that. For values of x outside the range of data. So you collect data and it has x values, and maybe the x values range between 5 and 15, right? So you only got people's ages between 5 and 15, right? And that built your model, right? That built your straight line, and that's a nice line. And then you use it, your model, your equation. So if you, I'll put a little word up here to remind you, model just means this equation. But you use it for a value of x that's outside the range of the data. So let's give you some examples of extrapolation causing problems. So you collected data on 5 to 10-year-olds, and the data you collected was x was their age, right, and y was their weight. Okay. And you did that, and you get, would you agree it's you could have predicted it would look like that? Would you agree? The older you are, the heavier you're going to be, right? 10-year-olds tend to weigh more than 5-year-olds, right? And you get your equation, and the equation happens to be y hat equals 15 plus 10x. So the predicted weight is 15 plus 10 times the age, right? And these are going to be very fat babies, but forget about the details, right? That's the equation. Now, you can use this equation to predict the average age of a 6-year-old, a 10-year-old, a 9.5-year-old, and you will get pretty good predictions. Extrapolation is when you use it for an x value outside the range of the data. So you use it for a 20-year-old. Oh, what will a 20-year-old weigh? Well, you've got your formula. The predicted weight for a 20-year-old is 15 plus 10 times 20, and it ends up being 215. A little bit in the big side. So you use it for a 70-year-old, and the weight, the predicted weight, now becomes 715 pounds. Do you see the effect of extrapolation, of using your model, your equation, to predict things that weren't from the original data? The original data was only collecting people from 5 to 10, right? That is a common mistake that people make with regression lines, is they've got this lovely equation and then they start putting values of x that should never be used, right? Does that make sense? That you could, in Casey, and the reason why it can be a dangerous thing to do, and very often is aren't you making a prediction that this straight line pattern continues forever? In other words, the older you get, the heavier you get. And don't we know that that isn't true? It's not linear, after about 18 or something. Just show you another example of that issue. Let's do one with negative data. So this is number of cigarettes per day that a person takes. And here is going to be your life expectancy. And starts up here about 83, and the data goes down. Let's suppose you collect data from people who don't smoke, which is 0, and it goes 1, 2, 3, 4, 10, 15, 20. And you collected data on people who smoke 10, 20, 30 cigarettes a day. And you can collect this data reasonably easy. You know, sometimes what they do is they ask doctors, for instance, to look at their patients and find out what they smoke, right? Because one of the questions, you know, do you smoke? And if you say no, that's fine. But if you say, yeah, I smoke, aren't they probably going to say, well, how many do you smoke a day? You know, are you a 2 cigarette a day person, you only take it with your coffee, or are you a chain smoker, right? Yeah, you know, there's never one out your mouth. Right, and they get an idea of that. And then eventually, as everyone does, they die. And so can't you collect this data? So it is doable, you collect. And it looks like, well, I'll put some more numbers here. And the predicted life expectancy, how long you live, is given by 83 take away 0.5 times the number of cigarettes. Right? Now, if I use this model and the way it was designed, I could say, oh, okay, I've got a new patient. He came in from Texas and now he's my his doctor. And I ask him, does he smoke? And he says, yes. And you ask, and you say, how many do you smoke? And this first person said that he smokes 10 cigarettes a day. So you would be able to use this formula and you'd go 10 cigarettes a day. And you would say to him, well, you'd probably say a couple of things to him. First thing you could say to him is, well, you know, people who smoke like you do only live to about 78. Can you also say, you're probably going to knock 5 years off your life if you keep doing that? And in that context, that is totally the way this should be used, isn't it? Because isn't 10 cigarettes in the range of data? Suppose someone else comes in and they say they smoke 100 cigarettes a day. Surprising that they're alive, but I'm doing this as an exaggeration, right? Then according to, oh, isn't 100 outside the range of data, right? So this is an extrapolation one. Right? You would say that their predicted life expectancy is going to be 83 times away 0.5 times 100. And you would come up and say, hey, your life expectancy is 23. And he's going to say, well, that's good because I'm already 40. Right? You can see that the predictor isn't good anymore. So be well aware that when you see a formula like this that's being used in linear regression, have a really good look at the data to see the range in which the information was collected. And if someone's asking you to use this formula, this model, for numbers that are bigger than 30, you should be very wary, feeling that they're accurate, right? There's a good chance they might be, but isn't there just as good a chance that they're totally wrong? Right, so don't fall for that one. You know, if this was data telling you about the number of people who are unemployed, right, and this was time, if this equation kept on going, wouldn't there reach a point where nobody in America was unemployed? Right, imagine this line, wouldn't it eventually go under the x-axis, nobody unemployed? But if you kept on going, right, more and more days, wouldn't you get to the situation where there was not only was nobody unemployed, wouldn't there be jobs where nobody was left to get them? Okay, right, everybody's got a job, and there's more jobs. You see, that's stupid, right? That isn't how economies work, right? Yet politicians are forever telling me that this is going to happen in the future. And what they are doing is they've collected data up to today or last year. And then they're saying, oh, I'm going to use that to predict the future. Don't use correlation, don't use regression to predict the future. It's very dangerous, right? If I really knew what was going to happen tomorrow, couldn't I become a millionaire and spend money by buying stocks? And if I knew what the economy was going to be next year, couldn't I make money on the stock exchange? So don't believe people who tell you they know the future, because they don't. Are we good with that concept? That seem reasonable? Extrapolation is a bad idea. Oh, you probably wouldn't see this term, but just for completeness, see if you use numbers in this range. The fancy word for that is interpolation. And if you use numbers like over here, it's called extrapolation. Inside, interpolation. Yeah. Exterior, outside, extrapolation. So in case you see those names, interpolation is good up to a point. So let's show you another problem. Would you agree that this data is curvilinear, right? It's curved, right? Not straight. Now, you could plug that into software and it will give you a straight line. And you know, it'll give you a line, maybe something like that, right? And it'll have an equation. Oops, that'll be a negative, won't it? So let's try that again. It'll have an equation like that. And it'll have an R value. Maybe that. By the way, 0.6, isn't that just 36%? Not a great fit, but of course it's not. It's curved data. Now, if you use a linear function, right, a linear model for data that's curved, even if you use it in the range that the data's in, let's suppose you collected data from 0 to 50, isn't that model going to be disproportionately wrong depending on where you find it? If I used it for 20, would you agree that this model's not going to be too far away from the data? But what happens if I try to use it at 50? Do you see the difference? You see how big those errors are? So if data is curvilinear, your predictor, right, your y hat, won't be the same for different values of x. See, if it's normal linear data, right, by that I mean really is straight data. Can you imagine your straight line going through it? Won't it not really matter which value of x I picked? I'll be out, but won't I be kind of out about the same amount each time, right? No particular value of x is going to be worse than the other. In curvilinear data, aren't you going to have a problem at the ends where the curve happens? And if you try to use that, can you imagine that your predictor is miles out? So this isn't extrapolation, right? Aren't I using values of x in the range of the data? It's just that the data is curved and you shouldn't use it. Another problem. So what's that? Guess the moral of that story is don't use lines when the data is curved. That makes sense? Just don't use lines when it's curved. I don't care if it, don't use lines if it's like wavy or any kind of curve. What's that one? This one's a little less obvious. Here is some weird data. I've color coded it just to emphasize it, but it would just be the same color if you plotted it. Now, if you put this into software, you would get an equation for a straight line. And the straight line, I've made these roughly parallel, would end up being there. Oh, guys. Would you agree that this model, this straight line, is not very good for this data set? In fact, doesn't this data set consist of two distinct sets of data? The green dots and the red dots. Can you imagine that the green dots were guys and the red dots were women? Right. So what the moral of that story is, if your data looks like it's separated into two distinct groups, as it is here, then what you probably should do is do two separate models. Shouldn't you do a model for the men and a model for the women? Right. Body chemistries of males and females aren't exactly the same, right? Women have different hormones and men have different amounts of hormones, I should say. And well, here's a simple thing. You know, women live longer than men. Right? So if you were doing life expectancy, wouldn't it be a better idea to do a life expectancy on how you smoke cigarettes and how long you live for women, and then have a totally different set of data for men? Because you would have the effect of various things. Totally sexist, but it is true. I believe if it's true, it's not sexist. Alcohol affects women's bodies more than alcohol affects men's bodies, right? So if you give a male 4 whiskeys and you give a woman 4 whiskeys, it's different. And there are a couple of reasons for that. Men metabolize alcohol a little bit quicker than women do. And aren't men typically more muscular? And alcohol affects muscular people differently than people who are softer. I'm trying to think of ways around it. So what you got to look at is, when you're analyzing your data, don't always treat that it's one set of data. There might be a better way for you to separate it. Because if you did, instead of getting a really bad formula with an R of 0.3, couldn't you get 2 really good formulas, right? This straight line, and get like a 0.9 and this one, and maybe get a 0.85. Wouldn't it be much more accurate because of that? So there is another kind of mistake that people make, and that is use one set of data instead of separation. We've only got 2 more topics and we are done. We'll have a look at homework questions and call it good. You've seen this phrase before, because I remember doing it. Oops, wrong way around. Correlation is not causation. And try to find the spelling. Called confounding. So, and connected to that, a thing called a confounding factor, sometimes called a confounding variable. So remember the story where I did TVs and how long people lived? And it's not that there's a strong correlation, right? A strong linear connection between that. But the real reason is not that TVs cause you to live longer. Wasn't the answer. That TVs were just measuring how wealthy a country is, and wealthy people from wealthy countries tend to live longer than people from poorer countries, right? That kind of thing. That is what we call correlation. And the guy that's called a confounding variable is, if you like, the real reason for the relationship. So in the one that we did, and just to remind you how it went, wasn't it the number of TVs was the x-axis, and how long you lived was that one. And didn't we say the data kind of looked like this? And it is actually, the real data looks just like that. Each one of these dots is a country, right? More TVs, you live longer, right? In that case, the confounding variable would be the wealth of a country is the real reason that people live longer, right? Or the major reason that it would be. So let's go hunting for some more of those situations. So let's suppose that the x-axis, the explanatory variable this time, was what? How much coffee they take a day. And this one is their blood pressure. Now, this probably isn't true, but let's pretend it is, right? So someone collected data on how many cups of coffee you drink a day. And there's some people who drink none, and some drink 1 a day and 2 a day and 3 a day, right? And all that kind of thing. And they got their average blood pressure, and they found out that it was a positive relationship, right? And they then have an article or a newspaper story or something on the TV that says, new report, new survey is out that coffee increases your blood pressure. So drinking coffee is bad for your blood pressure. You ever seen stories like that that come out from time to time that doing this is causing that, right? The old, this is causing that, the causation thing. Now, it may well be true that coffee does make your blood pressure go up, but there could be another reason for that. Can anybody come up with a different reason? That would be the confounding variable that could explain why people who drink more coffee do have higher blood pressure. I can think of one, but I don't want to put my answer in. Can you think of one?
Amount of exercise, maybe.
So people who drink a lot of coffee don't exercise, and don't exercise affects blood pressure? Could be. Any others?
Maybe they're more stressed.
What was that, David?
Maybe
Think-
people who drink more coffee are more stressed.
God, you're a mind reader. That's what I was thinking. Right? That if you drink a lot of coffee, it's probably because you're stressed. And would you agree that stress probably does make your blood pressure go up? So isn't the coffee just another measure of how stressed you are, right? If you're really stressed, you drink 5, 6, whatever cups of coffee. That could be it, right? There is, can't think of another, but if anybody's got another one, that's good. If I wanted to test that theory, wouldn't I forget about the coffee that they take and go back to those people and find some way of measuring how stressed they are? It is possible to do that. You give people a scale of 0, I'm chilled, man, to 10, God, I'm ready to explode here, right, whatever. And you can give them a little scale and they pick the number. It's like self-identifying. If you want to be a little bit more sophisticated, what you do is you give them like 20 questions, and the answers to these questions. If you're more stressful, you tend to have stronger opinions or answers to certain things. You can do it that way. Anyway, last chance. Has anybody got another reason? I'm not sure. Can't think of one right now. Okay, here's the last one of this type. So the explanatory variable is just years. So, right, so it's the year 2000, 2001, 2, 3, 4, 5, 6, 2021, right? So the year is the explanatory variable. And how much they spend on beer. And they have discovered, at least in my story, this would probably be true in Scotland, right? And, you know, over a 20-year period, they asked various people, how much do you spend on beer? And this is what you got. And someone could interpret this data and say, ah, Scottish people are drinking more beer. What could be another explanation of this relationship?
Inflation, stuff's
Yeah.
more expensive.
Yeah. Can it just simply be, you know, things go up 2%? Wouldn't you buy the same amount of beer, but you end up spending 2% more on it? That could be the reason. Couldn't this just be a measure of inflation and nothing to do with America? And the reason is because the how much you spend is the problem, because isn't that money, and money can be inflation. Now, if this was changed to how many bottles of beer you drank a week, wouldn't the inflation not be an effect there, right? In fact, if that was the case, wouldn't this be very good evidence that people are drinking more beer? Right? So be aware that if you're trying to find a relationship, to make sure that you do your X, guy, you choose your X, what you measure for X, very carefully, right? To avoid a confounding variable. Story I want to tell you, and then we'll look at the homework questions. Well, don't have much to do, but I went to Glasgow University. That's where I got all my degrees, and I was in a statistics class, and the professor that was there told us about what would you call it? A clinical trial. There you go. Prostate cancer in men. And it was done, I believe, if I recollect, it was done in Denmark. Now, typically what they do with a cancer research like this is that they have two groups of people. One of them get all of them have prostate cancer, but half of them get whatever the treatment is at this present moment, right? The chemotherapy, whatever. And then the other half got the new drug. And because this pharmaceutical company hoped that this drug would reduce the prostate, or maybe even eliminate it, right? Which is fine, that's what they did. And typically what happens in a trial is that nobody knows what the treatment is, right? So the patient doesn't know whether he's getting the old treatment or the new treatment. So if it's a pill, you just get a pill that looks like the same as the other pill, right? The doctors who are treating those people are not even told what treatment they're getting. Is your patient still on the old pill or the new one? Because the pharmaceutical company provides all the medication, right? All your doctor is doing is keep an eye on your health. And what they tend to do in these trials is they look at the success rate of both groups. And if the new drug is more successful, right, won't that come out with fewer people have died of the prostate cancer, or the size of the prostate cancer is being reduced? Right? And what happened was that after about 2 months of this clinical trial, which was meant to last for 6 months, after 2 months, the data was coming in and it was horrendous. The new drug, in fact, instead of reducing the cancer, was, for want of a better word, agitating the cancer. It was making it grow faster and more virulent, and people were dying at a much quicker rate than the control group, right? The ones that got the old group. And what should have happened, because the data was there, is that they should have just quit the trial and said, this drug's not working, you know, and that happens, drugs don't work. But the pharmaceutical company had invested so much money into this, like the company, that was their main, you know, drug that was going to make them billionaires kind of thing, insisted in continuing the trial until the 6 months was up. because they were hoping that at the beginning it would be kind of like that, but after a few months it would then have a good effect, right? It's a bit like the drug's pretty rough at the beginning, but if you can hang in there, it'll work in the end. And but I guess the moral of that story is that when you see data and it's telling you bad things, so if you imagine this data is pointing down the way, shouldn't you just quit? Don't say, well, I hope it curves up again. Not a good idea. So even in those days, now how can you get away with that? Well, in certain countries in the world, you can get away with all sorts of things. In fact, if you're in a clinical trial, don't you sign a little waiver that basically says, if I die, can't sue me, right? And you kind of need that, because if you don't have that, won't nobody ever do a new drug trial? Right? And you have to have failures to have successes. Right. For the few moments that we've got left, really all I'm going to do is do a quick scan through the homework questions just to show you what they look like. Start at the top. There we go. The early questions are all about correlation coefficients and which ones can work and which ones don't. So remember, R has to be between -1 and 1. And isn't R squared between 0 and 100%? And then they go on and say, look at this data. How does units affect things? Well, haven't we talked about it? Don't units have no effect on the value? Won't the R value still be positive 0.95 if you measured in inches instead of feet? We've done data about which ones are strong, positive, and negative, which is all that. If I tell you R squared, or sorry, wrong way around. If I tell you R, can't you find R squared? Now, here's something I should have shown you. I think I did, but I'll do it anyway. Here is a set of data, right? And you're going to take a regression line. And how would we do it? Well, if you hit salt, there are only, I think, 2 questions like this, but I'm glad I got it. Here is your data. Hit the regression line, because we have done this part. And the first variable is, say, latitude, and the second variable, say, was August temperatures. And you see your little guy, maybe shrink him back a little bit. You see it? Now, if you want to see your regression line, yeah, remember we're doing that. Now, if you're asked for R squared, can you see it? It's that tiny little decimal at the bottom. Let's make it big again so I can see it. If the question says, what is R squared? Won't that be 60.95% if they want it as a decimal? And who do you think this guy here is?
R, just R?
Yes, yeah. I wish they just called it R, but I mean, it is R, right? Because I've told you, right? Does this make sense that 0.78 is definitely pointing down the way, right? So you can tell that way. And that's the end of that. And then we have the effect of outliers, right? What would this outlier do or whatever? Oh, here's a good one. If you do data, this data is curvilinear. And the reason I know it's curvilinear is if you're just using common sense, if you are a golfer and you're doing putting, right? The percentage of success when you're 10 feet away, about 40% of the time you'll putt it. But as you are further and further away, doesn't the chances curve downwards? Isn't there always going to be a chance, even at 70 feet, that you're going to get lucky and get it in? If it was linear, wouldn't there be a number where here at 40 feet, nobody ever putts, a hole when they putt, right? So I would assume that this is data, which that's what that's telling me. And there's a regression line and extrapolation. There's another one showing you some extrapolation, and then a couple of stories about causation. So I'm pretty sure I've covered that all. And last name and bye-bye. Sorry for keeping you a few minutes over time. So last name, and bye-bye. And I'll hang about if any of you have questions. We learned some cool stuff again today. So the next time you see a politician telling you something and he's got some data and he starts doing extrapolation, you're going to go, I'm not so sure. Okay, Daniel, do you have a question? If not, I'm out of here.